Good morning and welcome everyone to this 16th edition of our virtual seminar on precision physics and fundamental symmetries. My name is Stefan Ulmer. I'm a chief scientist at Riken and spokesperson of the base collaboration at CERN. It's a great pleasure to welcome today's speaker, Peik, who is the head of the Time and Frequency Department at the German National Metrology Institute, PTB Braunschweig. Eckhard studied physics at the universities of Göttingen and Munich, obtaining his PhD degree in 1993 from LMU Munich for experiments with laser-cooled trapped ions and first steps towards an indium plus optical frequency standard in the group of Herbert Walter. Then from 1994 to 1996, he was a postdoctoral Marie Curie Fellow at ENS in Paris, working on laser cooling and quantum effects in cold atoms with Christophe Salomon and Claude Contamouji. Returning to Munich to LMU and the Max Planck Institute for Quantum Optics in Garching, he worked on the advancement of the Indium Plus project, the development of novel traps and first optical frequency measurements of a trapped ion from 1996 to 2001. In 2001, he was appointed at PTB in Braunschweig as a staff scientist and became the head of the newly established working group, Optical Clocks with Trapped Ions in 2003, pursuing two main projects, the Ytterbium Plus single ion optical clock and the thorium nuclear clock. By the way, Eckhard, together with his colleague Christian Tamm, is the first person which proposed the use of this study of this nuclear clock. And then since 2007, he's the head of the Time and Frequency Department at PTB. In 2019, he became co-director of a Max Planck Riken PTB Center for Time Constants and Fundamental Symmetries. And Eckhard, we feel honored that you agreed to give a talk in this seminar series. We are very much looking forward to your talk, and now I leave the audience to you.
Thank you, Stefan. Good morning from my side. Yeah, it's a big pleasure for me to participate in this seminar. I would start by thanking the organizers, Stefan, Christian, and Klaus, for arranging this series in this unusual time and for giving me the opportunity to participate here. It's a great pleasure for me. So the subject of my talk is from the broad range of the activities of time and frequency at PTB here. It is really focused on questions of fundamental research, on the development of optical clocks of the highest precision, and on tests of fundamental physics, tests of the equivalence principle. So this slide introduces this twofold motivation for our work. So we are a National Metrology Institute. So the basics of metrology is, of course, our key business. So we have the duty to define and realize the base units. You are aware that last year there has been a major reform of the SI system, where the base units have been linked to fundamental constants. It was mainly a change for the kilogram, for the electrical units, for the unit of time, for the second. And nothing changed practically. It remains linked to the cesium hyperfine frequency. But in the new system, so conceptually, the importance of the unit of time is underlined, because now the other units are linked via fundamental constants like the speed of light or Planck's constants. And these constants contain the second in their unit. And so it is important to have the very precise realization of the second as a cornerstone of the SI system. So this is some of the outline of the metrology aspect of our work. And then besides, and what I will also speak about today, is the aspects of fundamental physics. So these clocks are so very precise that there is a strong motivation to use them in experimental tests of fundamental principles of physics. What we may call searches for new physics, so motivated by ideas about quantum gravity, about finding a unified framework between the fundamental interactions and finding physics beyond the standard model. And the approach of these experimental tests is always to make precision measurements that look for effects that would not be predicted by the standard model, or that would somehow quantitatively violate predictions of the standard model. I've listed here a few prominent examples like time dependence of fundamental constants, test of the universality of the gravitational redshift, also a typical clock experiment. And today I will just focus on one recent example from our laboratory, which is a clock comparison test of Lorentz symmetry. For a deeper treatment of the subject, I can really recommend the review article mentioned by Stefan already, by Mariana, and it will certainly be great that she will be giving a talk in this series on Thursday. The atomic clocks have made really big progress over the last, say, 20, 30 years by the introduction of the methods of laser cooling and trapping, so that it is possible to work with cooled and trapped atoms, reducing Doppler broadenings and shifts, and having atoms available for long observation times. So this slide briefly summarizes the three main systems that are used and that are under investigation today in the big institutes. Like PTB is working on all of these three subjects. On the left-hand side, you can see the modern version of a cesium clock, which is a cesium fountain. So starting with laser-cooled atoms, these atoms are thrown upwards against gravity, and on these free flights, they pass through a microwave cavity where their hyperfine ground state resonance is interrogated. And these are the most precise cesium clocks that realize the SI second, the basic definition of the unit of time. And then we have the active research work on the optical clocks with trapped atoms, and there are the two main directions of using neutral atoms trapped in an optical interference pattern in an optical lattice at the so-called magic wavelengths, where the light shift induced by the trapping laser beams does not shift the clock frequency. This is an active field of research. And the other competing direction is to use trapped ions, charged particles in electrodynamic traps, and also to cool them and to use spectroscopy of forbidden transitions of these ions as a reference of the clock. And the latter system is actually the one that I will focus on in my talk today, because this is also the activities going on in our group. So the seminal ideas for these optical clocks date back to the 1970s already. Hans Dehmelt made really visionary proposals at the time, uniting the key ingredients of these trapped ion optical clocks. So one uses a Paul trap, radio frequency trap. You can see here a classical version with 3 electrodes about 1 millimeter size. And this is used to trap single or small number of ions. The ions are cooled by laser cooling. So the combination of cooling and confinement brings them to the Lamb-Dicke regime. You see here such a false color picture of a Coulomb crystal of 5 ytterbium ions. The clock operation that I will speak today is really focused on a single ion, like the one sitting here in the center. Single ion means, of course, quantum effects, relatively weak signals, and there has been this other important proposal by Dehmelt how to do spectroscopy on such a system via the observation of quantum jumps. So one always has such a V-level system where from one ground state there is an allowed transition that is used for the laser cooling and the fluorescence detection. And then there is a narrow reference transition of the clock. And each time that this transition is driven, the electron is shelved in the metastable level. This becomes observable as a dark period in the fluorescence signal observed on the cooling transition. And this very efficient quantum amplification mechanism allows to do high resolution spectroscopy on a forbidden transition, maybe scattering only 1 photon per second in a single ion, but this provides the data, the signal to noise ratio in order to obtain very narrow spectra of forbidden transitions. So obviously the lines can be very narrow because the ion can be observed for a long time. Broadening mechanisms can be controlled and eliminated very efficiently. But there is noise, or the signal to noise ratio is of course determined by the fact that we're just observing a single particle, so there is quantum projection noise, and one has to average over several cycles in order to obtain such a spectrum. But obviously the method is suitable when there is narrow forbidden lines, and especially those that are interesting that do not interact very strongly with the electric field, because the electric field is what we use for trapping. So the specific example that we are studying here at PDB is ytterbium plus, and I'm going to explain a little bit in detail why this ion is so interesting for us. It's not interesting only for us. It is maybe one of the most popular ions now used in ytterbium in experiments, both on spectroscopy, fundamental tests, and also on quantum logic. So we are working with the 171 isotope. It has a nuclear spin of 1/2. This is why we have selected this isotope. So it means that we have coupling between a single valence electron with spin 1/2 and a nuclear spin of 1/2, and this gives a very favorable hyperfine structure. All the transitions that are needed for cooling observations, the reference transitions of the clocks, can be driven by diode lasers, which is convenient for the operational reliability of the clock. I mentioned the nuclear spin 1/2, the mass is relatively high, so cooling it provides low motional frequency shifts. And what is really special about this, about the ytterbium, there is 2 reference clock transitions in this ion. So it is shown here. So basically from the S ground state, one can drive electric quadrupole transition, promoting the S electron to the outer D orbit, which is quite a common type of forbidden transition. And then in addition, we have a forbidden transition where the 4F shell that is closed in the ground state is opened. A hole is created in the 4F shell, and this additional electron fills the 6S shell. This is a very long-lived state. The decay to the ground state only proceeding by electric octopole transition. And it has very interesting spectroscopic properties for the use of the clock and also for the fundamental tests. So here this table compares a few selected properties of the quadrupole and of the octopole transition. The natural line width is very different. So for the quadrupole, the natural line width is a few hertz. For the octopole, it can only be estimated. The estimate is that the radiative lifetime of the excited F state is several years, so one would obtain a nanohertz natural line width. And now what's very important for the clock is that with respect to external perturbations, the sensitivity of these 2 transition frequencies is very different. So we have in general the quadrupole transition, which is in general much more sensitive than the octopole transition. 2 examples are listed here. So for example, the quadrupole shift due to the coupling to external electric field gradients is related to the quadrupole moment of the excited state. And while for the D state, the upper state of the octopole, it is like 2 in units of elementary charge times Bohr radius squared, the usual scale of an atomic electronic quadrupole moment. For the F state, it is much smaller because this F electron is closer to the nucleus and also somewhat protected by the spherically symmetric 6s electrons. Similar for the another example here, second order Zeeman shift, also a significant factor like 25 smaller. So it means that we have in the same ion here one transition that we can use for an in situ diagnosis of these perturbations. And then if we know the ratios of these sensitivity coefficients precisely, and we have made some efforts to measure these, then we can infer corrections for the much smaller perturbations on the octopole and realize the octopole transition with a very high accuracy. And the lowest line here describes the number alpha sensitivity, alpha the fine structure constant. So this describes the sensitivity of the transition frequency to the value of the fine structure constant, assuming that there would be hypothetical changes. And you can see that also these values are very differently. They are about 1 for the quadrupole transition. There's negative for the octopole, negative because it is in whole state, and the value is 6, significantly bigger than for the D state, just because this 4F electron is closer to the nucleus. It's more strongly relativistic. It means that measuring the frequency ratio between these two transitions would be quite a sensitive measure for the value of the fine structure constant. So based on these advantages for the octopole, we have in 2016 compiled a first high accuracy uncertainty budget for this clock, and obtaining a total systematic uncertainty of 3 times 10 to the minus 18. I'm not going into the details of this uncertainty budget. You can see it is composed of several contributions on the order of 1 or 2 parts 10 to the minus 18. So there are several handles that we will be working on to improve the system, and I will speak a little bit about some of these details. The first column here shows the overall shift that these effects is inducing, and you can see, and this is a nice feature of this clock, that the overall shifts are already small to start with. So the overall, there is a shift of about 1 in 10 to the minus 16 for the clock operation, and you can see there is 2 contributions here from black body radiation and from a second order Zeeman shift contributions, especially the Zeeman shift, which we can control quite well. So this was the uncertainty budget we compiled in 2016, and then we made efforts on one hand to verify, to test this uncertainty budget, and of course also to improve it. And I'd like to give you a little bit an impression of how it looks in our laboratory. It's a little bit of a special, unusual laboratory. It's a big room, nearly 300 square meter, the so-called clock hall of PTB. And I'm showing this picture to introduce to you 3 generations of ytterbium clocks that we have been developing over the time. So we started counting them. There's ytterbium 1, 2, and 3. Different generations of ion traps in one laboratory. We have a frequency comb here for linking the different optical frequencies. And we have here on the left-hand side a quantum technology project called OptiClock, where the aim is to build an ytterbium single ion clock that is robust and autonomous for operation in user laboratories outside of a major metrology laboratory. But here we are in a metrology laboratory. You can see this. We are standing right next to the cesium fountain clocks of PTB, CSF1 and CSF2, the 2 primary clocks that are realizing the SI unit at PTB. And so you can see we are very closely linked with these activities. So in second half of 2017, we started to do a long-term comparison between the 2 oldest generations, ytterbium 1 and ytterbium 2. These 2 clocks are physically quite different, so they are making use of different generations of ion traps, the old classical 3-electrode Paul trap and a more modern end-cap trap version. We're trapping a single ion each. The experiment is sharing the reference clock laser that drives the octopole transition, which is a special system in the sense that it derives a very good long-term stability and low noise, narrow line widths by making a reference to a cryogenic silicon cavity that is developed here at PTB in the group of Uwe Ster, and that is available for us as a long-term reference. And then this laser light is guided through different acousto-optic modulators in order to have two independently tunable beams that interrogate the two ions. We try to make this comparison independent as possible. So we are using independent traps, independent interrogation methods also. So I did not yet mention in detail that this octopole transition is prone to a light shift because it is so strongly forbidden. The intensity needed to drive this transition is somewhat higher. And so this reference laser itself produces a light shift, and we are controlling this effect by using modified Ramsey methods. I will not go into the details here today, but just to show you, we are also using two different interrogation Ramsey schemes in these two clocks. So to really be sure to have relatively independent operation of the two clocks. We took data for several months in the second half of 2017. This plot here summarizes all the data that were taken. It was more than 1,000 hours. And you can see here the red line indicating the overall average frequency difference between the two systems. And we were very happy and relieved to see that this difference is very close to zero. The difference is less than 2 millihertz on this optical frequency, well within the 1 sigma uncertainty of the combined system that is indicated here by this shaded gray area. So in terms of numbers, we observed a relative frequency difference of about 3 parts in 10 to the minus 18, and consistent with the overall combined systematic uncertainty of about a bit less than 4 parts 10 to the minus 18 at this time, and 2 parts in 10 to the minus 18 statistical uncertainty. The plot here on the right-hand side shows the instability of this comparison. It is dominated by the single ion quantum projection noise. But the nice feature is that you can see that it averages down continuously for the long averaging time to below the level of the combined systematic uncertainty. So this gives us some confidence that we don't have long-term drifts or uncontrolled fluctuations in the system. So this is a key metrological message of this comparison, showing that the two clocks agree to within their uncertainty budget. And now, taking so much data, of course, we were also asking ourselves what else could we do from it, and we found that it is very nice to use these data as a test of local Lorentz invariance, one test of the equivalence principle. Here we are following proposals by Alain Kosteletsky and colleagues using a so-called standard model extension, and indicating that violations of Lorentz invariance and other CPT violations should be and may be searched in all the interactions of the standard model. So basically, we are somehow doing something that could be described as a Michelson-Morley experiment, but not for photons, but for electrons. So the question we are asking here is the electrons dispersion relation isotropic in space? Of course, the electrons may have different velocities, but the speed of light, c, enters into the dispersion relation. And the question is it the same speed of light as for the photon? And is it also a universal constant, or does it have a hypothetical distinct orientation that would be apparent if one thinks of the electron in a box, in an anisotropic box, and then turning this box, one may ask, does it change the properties of the electron? The box that we are investigating is the excited F state of the ytterbium ion, and it is suitable for this type of study because the momentum wave function in this F state is very elongated, very anisotropic. So turning it really makes the system distinguishable, and it is comparing these two orientations should make the system sensitive to Lorentz violating effects. And how the experiment would be done would be via measuring clock frequencies by driving the transition between the S ground state and the F excited state. So the ground state is isotropic. The excited state has this orientation anisotropy. And we are using the two clocks that we are comparing with their quantization axis oriented in different directions. Quantization axis is determined by a static magnetic field. And so we can compare two clocks with different orientations and compare the two frequencies realized here, and frequency offset would indicate a Lorentz violation. And the way the experiment is done, in order to be able to detect a very small frequency difference, we are using kind of a lock-in detection by following this frequency difference in the rotating frame of Earth. So if there would be a hypothetical preferred cosmological direction, then in operating the clocks for many days, we would see a Lorentz violating effect as a sidereal dependence of the frequency difference between the two clocks, and that's why this type of experiment has been called a Michelson-Morley experiment. So think of the two clocks on a rotating table sharing one frequency, and then as the table is rotated, the frequency difference is looked for. This type of experiment and this concept has been pioneered in the group of Hartmut Heffner in Berkeley. He performed an experiment with entangled calcium ions in 2015. I should also mention experiments on dysprosium in Dimitri Butka's group. And for us, it was important that Vladimir Juba and colleagues here pointed out in theoretical work that the F state of the ytterbium would be especially sensitive to this type of effect. And this gave us the motivation to study it in the comparison of the octopole clocks. So here you see the same data set, the like more of 1,000 hours of data, but now in an analysis where we look for periodicities. In this data set in the frequency difference, this is done here in a method called a LOMP periodogram. So the data set is analyzed for different periods, starting from a period of a few minutes, extending to several days. And here in this experimental data set, these red lines indicate probability levels for finding a periodic signal. And this would give the probability in a completely uncorrelated white noise spectrum. So it gives like an indication of the background noise level. And so here for 50% significance of a periodic, one would expect the peak level here. And you can see, yes, there is 2 events. But if we ask for a 3 sigma significance for 5% significance, there is no significant peak. And from this, we can deduce the statement that our signal does not contain any significant periodicity, neither at the sidereal day and also not at other periodicities here. So the full quantitative analysis you can find in this publication. I'm just summarizing here that it gave about 100-fold improvement on the parameters characterizing possible Lorentz invariance violations for electrons. So this was a key result of the fundamental test of this clock comparison. You may note data was taken some time ago already. So what else did we do, and what did we do in addition to these measurements? So we worked, of course, on improving the uncertainty budget. And here it is again summarize the uncertainty budget I showed you already for the first generation octopole clock. And you can see here in this table that many of the uncertainty contributions are related to the ion trap setup, like to the temperature of the trap for blackbody radiation, for example, or also to the temperature of the ion, like the ion heating rate that goes into the second order Doppler shift. That was one of the bigger contributions to the uncertainty. So from this, we decided that the most helpful approach to improve on this clock would be to build an improved trap. And this is the third generation ytterbium 3 that we have built. And it attacks a mixture of all these different effects. I'm going to speak a little bit about the detail of the blackbody radiation. So the blackbody radiation shift of the ion frequency is produced by the room temperature environment of the trap, and it produces an AC Stark shift of the ion frequency. The AC Stark shift can be written like this. It depends on the differential polarizability and of course on the electric field, which is a temperature dependent quantity. We have these two contributions here, and in our 2016 uncertainty analysis, the two contributions from the scalar polarizability and from the temperature contributed about equally to the total uncertainty. So we decided we should work on both effects in order to make an improvement. For the temperature, we are faced with a situation that the ion inside the trap is exposed to an inhomogeneous blackbody radiation field, because the ion trap structure is assembled from different materials. There is the electric fields, current flowing there, some materials are heating up. So quite some effort was done in order to analyze and quantify the effects of this inhomogeneous temperature environment. You can see here some pictures taken of the ion trap with an infrared camera. The first generation trap here, the 3 electrode design, you can see here the infrared picture with the RF field off and on, and you can see, oh, there are some hot spots appearing. These are insulators, ceramic insulators between the trap electrodes. At the time, Makor machinable ceramic was used for these insulators, and Makor is now understood or known to have relatively unfavorable dielectric properties that lead to some RF heating. So these heated up the trap structure, and then the heat was only dissipated via conduction through the metal parts and leading to some inhomogeneity of the thermal environment. So in our third generation trap, we have made the whole metal construction more massive in order to have better heat conduction. And we have removed these low quality ceramics, replaced it by low loss fused silica spacers. And you can see it's not so obvious to see from the picture here, but we have a significantly more homogeneous temperature distribution, and also a smaller rise above room temperature from this trap. So we make some improvement here of the thermal environment. The other effect that we looked at is the uncertainty from the scalar polarizability. So this is the number, an atomic property that we have to know in order to do the correction on the atomic frequency. We are using data. We need to have this differential polarizability at about the 10 micron wavelengths of the room temperature blackbody radiation. We obtained this number by making light shift measurements at near infrared wavelengths with infrared lasers. And fortunately, so the theoretically predicted wavelengths dependence of the polarizability is completely smooth. There is no atomic resonances. And that's why we could predict it relatively well with like about 1 or 2% uncertainty. But we found a way to do better, and the way is to use another ion as a probe for this effect. And there is another ion, Strontium plus, where the polarizability is known about 10 times better than in the case of ytterbium. This is because strontium has a very special property outlined in this publication here by Periodogram and colleagues from the Canadian laboratory. Operating the trap at a so-called magic RF drive frequency, one can compensate the effects of the static polarizability Stark shift produced by the trapping field and second-order Doppler shift produced by the trapping field. And in this way, this is a way to measure the strontium polarizability very precisely. And our idea is now an experimental approach to use a linear trap to trap strontium and ytterbium together to expose both of these ions to the same infrared laser and then use strontium as a probe and to improve on the uncertainty of the polarizability for the ytterbium. Strontium has more advantages. It can also serve as a sympathetic cooling ion, so it will allow us to keep the ytterbium cooled for long interrogation times, obtaining narrower line widths. So we hope with this measurement to also reduce significantly the other effect here on the scalar polarizability on the blackbody uncertainty. And taking these effects together, this is another thing I should mention. So the strontium can be cooled, sideband cooled on what is called strontium clock transition here. It is a quadrupole transition. Strontium that will be used for sideband cooling, and it is close to the magic wavelengths of the ytterbium octopole. So this cooling light will not perturb the octopole clock too much. So that's why we also a factor why we believe that it is a good idea to combine these two ions. And here to sum up these prospects on the uncertainty budget, we have here the previous uncertainty budget from 2016. This is the improvements we made already during the clock comparison campaign. And now with these foreseeable improvements on the blackbody radiation effect, we believe that we will be able to lower the total uncertainty to below 10 to the minus 18 to go to the 10 to the minus 19 range. So you see, we are optimistic about further improvements of the ytterbium clock, and this is ongoing activities in our labs. So with this, I'd like to shift gears a little bit and to switch from the optical ytterbium clock to our more far-reaching, more speculative nuclear clock proposal. Also a research project that has been going on here for quite some time already, but it turned out to be experimentally really challenging. We don't have the nuclear clock yet, but I'm going to spend a few minutes to show you some aspects of the prospects that we believe to have with this nuclear clock. I'd like to briefly start by introducing what I mean with the nuclear clock. So it is very similar to the atomic clock that I have described and that is well known, but the laser oscillator here would be frequency stabilized, not to a transition in the electron shell, but to a transition inside the nucleus, to a gamma ray transition. And the strongest motivation here for this is to obtain higher precision, because the field-induced shift that I've spoken about to some detail in the ytterbium and in other electronic atomic clocks can be significantly reduced in a nuclear clock, and I will explain you in a bit more detail why this is so. And then there is two more aspects. One can also think of obtaining higher stability. Nuclear spectroscopy can also be done to very high resolution in a solid environment. One does not have necessarily to use laser-cooled samples, but one could do Mössbauer spectroscopy. And this would, of course, enormously boost potentially the number of nuclei that can be interrogated in comparison to the single ion or even lattice clock experiment. So it would promise potentially higher stability. And the third aspect I've put in gray a little bit here, nuclear physics, of course, characterized by higher frequency X-ray, gamma ray transitions, also one route to obtain potentially higher stability of a clock. But it would mean that we would have a very high stability X-ray or gamma ray source, which we do not have at present. So we are looking at a regime of very low energy physics, and it is available. Some nature provides us some very low energy transition. So this graph here shows a chart of nuclides. So the usual format, you know, neutron number here, proton number here. And the color code indicates the energy of the first excited nuclear state. red here indicating high energies. You see the structure which corresponds to the closed nuclear shells, the so-called magic nuclear numbers. Then the nucleus is very tightly bound, and also the first excited state has a very high energy. But here in this region of the heaviest nuclei, you see the color code turns green, which is the lower energy. So this is a region where we have the collective motion of heavy deformed nuclei. And here there are some lower excitation energies like collective rotations also, which are in the 10 keV range. So that's still a high energy for atomic physics. But there is one notable exemption, which is the thorium-229, which has an excitation energy of only about 8 electron volts, the lowest excitation energy that is known in nuclear physics. In terms of laser wavelengths, it would correspond to about 150 nanometer vacuum ultraviolet radiation. So that is the perspective to probe this transition with a laser. This has not yet been done, but we have learned quite a lot otherwise about properties of this nucleus recently. So this graph here summarizes a nuclear two-level scheme, the ground state, the excited states. There is some nuclear physics characterization. It is a magnetic dipole transition, not so strongly forbidden, lifetime a few thousand seconds maybe. And now the nuclear properties, nuclear moments are known in the ground state and also in the excited state. You can see the typical small scale for the magnetic dipole and electric quadrupole moment that is characteristic for nuclear transitions. The scale that is much smaller than for electronic transitions. The numbers indicated in red here have been recently obtained, like in the last 2 years or so, from a very fruitful European project called NUCLOC. This is here contributions from the group of Peter Tirolf in Munich and from our group. And this jointly together we measured hyperfine structure, and the Munich group recently measured this improved energy value, a very important result for the transition energy. The project was concluded last year, but I still recommend the website is still online. It gives a nice summary of literature. I recommend you this website if you would like to learn a few more details. Now a little bit some hand-waving reasoning of why is this clock potentially interesting for fundamental tests like I've been speaking about. And I give you some really hand-waving pictures here, and I refer you to these papers by Victor Flambaum, who has made pioneering seminal contributions to these proposals. He is the author of these 2 physical review letters that I'm citing here. But I'm just trying to give you here briefly a hand-waving picture. Why is it interesting to compare this nuclear clock to the other atomic clocks like the ytterbium, the cesium clocks that we have available? First, core difference for the nuclear clock, the transition frequency is not purely electromagnetic, but it's also determined by the strong interaction. So we have access to the coupling constants of the strong interaction. It also enters sensitively into these tests. And more important, it has been pointed out by Victor Flambaum that these contributions, both of the strong interaction and also of the Coulomb interaction to this transition energy, lead to a strongly enhanced sensitivity, because these contributions somehow magically must cancel for the transition energy. This is shown in this sketch. So these 2 nuclear states, the ground state and the isomer, they have nearly, on the nuclear scale, nearly the same energy, just differing by 8 eV. And how can this be? There is not today, nobody has really a microscopic picture of this nuclear structure, but what we know already is that the Coulomb contribution definitely changes on the 100 keV or maybe MeV scale. So if this changes on the excitation from the ground state to the isomer, then this change of the Coulomb contribution must be compensated by a similar and opposite change in the strong contributions, because otherwise the small energy difference would not appear. And now you can immediately understand this is a very delicate balance between these two states. And if this balance would be perturbed by, say, a change in the fine structure constant, it would have a drastic effect on this frequency difference. And a similar reasoning of a very high sensitivity can also be applied to this picture of the Lorentz violations. Again, very hand waving, I'm speaking here. So I've explained to you that the sensitivity of the terbium experiment becomes from the very elongated character of the electron wave function and from the high kinetic energy, from the closeness of this electron to the nucleus. And of course, inside the nucleus, we are in an even more extreme regime. We would be sensitive here to other massive particles, neutrons and protons, and energies would be way higher. So also one expects an enhanced effect on Lorentz violation. So very sensitive to the violations of the standard model, and also very precise. So that is what makes it a very promising system for study. I will briefly explain what is the basic, also hand waving again, the high precision of the nuclear clock can also be understood qualitatively quite easily. So we are driving a nuclear transition here between two nuclear states, but we are studying, of course, in an environment, in an electronic environment. But most of the electronic environment in driving this nuclear transition is common mode for both levels, since the electron structure does not change. So it means that all the shifts that we are worried about in the other atomic clocks that are coupling to the electronic properties would be common mode for both levels of the nuclear clock, and they would not change the transition frequency. And this holds for an important classes of shifts that are the limiting factors in the optical clocks that we are investigating with trapped ions, or also in lattice clocks. For example, the scalar quadratic Stark shift, including the effects of static electric fields, collision, blackbody radiation that I have discussed for the terbium. All this is largely common mode here for the nuclear clock. So what remains would be just higher order terms, tensor shifts, tensor Stark shifts, and they would also depend on the electronic quantum numbers, and there would be a choice of the electronic quantum numbers under which the nuclear transition is investigated. So this is a key idea, that one can investigate a favorable electronic condition that eliminates most of the frequency shift effects. This was the core of our proposal together with Christian Tamm. We published it in 2003. We proposed to use electronic levels of small angular momentum. And later there was a very interesting generalization in the group of Alex Kuzmic, Andrei Derevianko, Corey Campbell, pointing out that also stretched states of electron and angular momentum have the same favorable properties. So now I'm very widely projecting what does it mean for an uncertainty budget. Really don't take this too serious. It is just a projection for a nuclear clock based on a single trapped ytterbium 3+ ion. It can be laser cooled. And here I'm just eliminating from the terbium uncertainty budget that I've been discussing before all the E-field related shifts. And you can see that now the sum goes to the low 10 to the -19 range. So we would gain another significant factor and obtain a low 10 to -19 range of systematics, combined systematics for such a clock. I should notice a word of care. So this uncertainty budget is really the uncertainty budget of the proper clock. It does not contain all the relativistic effects, which would of course be the same for a nuclear transition as for an electronic transition. So we should worry about a second order Doppler effect in both cases. One should also worry in comparing and doing non-local clock comparisons. One should also worry about gravitational redshift. But we do not include it in the fundamental uncertainty budget of the clock because the SI, this is the point of view of fundamental metrology, the SI system defines property or proper time of the clock, but of course in clock comparison it does play a role. Now this is the bright prospects, and there has been, of course, very important experimental work in this field, and I refer you to the webpage and to the literature. I will just briefly, for the last slide, outline an experimental scenario that we and others are working on, because or to show you the difficulty. Why does a nuclear clock not exist? Yes, the proposal is nearly 20 years old. We have here a logarithmic scale showing frequency uncertainty or resolution of this nuclear transition. And this is where we are today in the uncertainty determined by gamma spectroscopy or electron conversion electron spectroscopy with an uncertainty in the 10's 0.1, 0.2 electron volt range, means 10 to the 14 hertz on a frequency scale. And this is where we want to go. We do not necessarily have to go to the millihertz 10 to the minus 18 uncertainty scale to be competitive, because of these high enhancement factors for the fundamental tests. We could also do very, very sensitive tests in the, say, kilohertz uncertainty range, but still it is like 12 orders of magnitude to go from the present level. And unfortunately, it is really a level of uncertainty. So we need to search, one needs to search for these very narrow transitions. So together with colleagues, experimental colleagues, Peter Tirolf from Munich and Thorsten Schumpf from Vienna, and with theory support by Mariana Safronova, we have jointly proposed the project to ERC Synergy, and we received a grant last year, so we will work on this on a bigger scale now. We have made this roadmap like a two-stage road towards laser excitation. We will first work on a gigahertz scale, like a 5 orders of magnitude improvement in the frequency resolution with a 4-wave mixing pulse laser system. And then from the gigahertz scale, we hope to be able to go to the kilohertz or hertz scale using then vacuum UV femtosecond frequency comb. So it will be a long-term, 6 years work project. But fortunately, because of the new character of this field, there is very interesting physics already at different stages. So also at this gigahertz scale already, we can learn very interesting things about isomer shift, hyperfine structure, about the interaction of this nucleus in different electronic environments. So it is a, I think, very highly attractive, but also very challenging, experimentally difficult project. So this brings me to the end of my presentation. I've summarized work from the atomic clock with ytterbium. We have operated this clock on 2 different reference transitions. You have compared 2 clocks, shown their agreement in the low 10 minus 18 level, have used this data for an improved test of Lorentz violation. We will also plan to use it, frequency ratio measurements for temporal variations of alpha. I'm not speaking about it today. The test, I've shown you another null result of such a test, so we don't find violations of the uncertainty principle, of the equivalence principle. We don't see new physics. So from this point of view, you may say it's a bit disappointing, but practically the null results are highly useful because we just obtain better clocks, we understand them better, and we are improving them. And we have these highly interesting systems on the horizon for fundamental tests and for new physics, like the nuclear clocks that I've spoken today, or the highly charged ion clocks that Pete Schmidt has spoken about here in the seminar today. Okay, with this, I'd like to close by acknowledging my co-workers, the teams in the working groups here, working on the trapped ions. The work recently pushed very strongly by Nils Huntemann, Christian Sanner, Richard Lange, and on the ytterbium clocks, and the Thorium team with my senior co-worker Maximo Chapkin and these colleagues, and we have very efficient and nice support from CERI externally and also now in Braunschweig. And we have funding from several agencies listed here. With this, I'd like to close and thank you for your attention, and I'm looking forward to your questions.